All right, so our next topic is momentum and impulse. It highly relates to the last few units that we've done. In our first unit of kinematics, we look at the motion of an object, its velocity, before and after something's happened to that object. And then the last two units of looking at energy and forces, we can see how forces and mass can change the acceleration of an object. As well with energy, we can see how the amount of energy in an object is also a function of, it can be a function of both not only mass, but in velocity. Now, what we're going to look at here is momentum, and momentum is defined uh, as the product of an object's mass and velocity. And essentially what they say is momentum is mass in motion. Now, the symbol for momentum is a Greek symbol rho, and it is a vector, so I'm going to put a vector symbol on it. And again, it is the product, which means we're multiplying mass and velocity. So I have my mass times velocity. And because velocity is a vector, and that's what makes our momentum a vector. Now the units for momentum, which don't really make much sense, but here are the units, is that we have kilogram meter per second, dot meter per second. There we go. So there's our units for momentum. And so, for example, we have a 22 kilogram pickup truck, has a velocity of 25 meters per second to the east. There's direction involved because, again, it's a vector. What is the momentum of the truck? All right, so again, when I'm writing down the information that I have, number one, the mass. Well, our mass here is, let's move this down so we can see, 2,250 kilograms, which is, again, our standard units. Our velocity, which is a vector, is 25 meters per second to the east. So we'll put an east in there. All right, and again, our velocity is a vector. And what we want to know here is our momentum. So again, I'm just going to use my formula that I have above, where again, momentum is equal to mass times velocity. And if I substitute my values in, all right, so I have, again, our mass is 2,250. Our velocity here is 25 meters per second east. All right, now if I multiply those two values, again, our momentum is going to be a vector. I multiply them and I end up with, let's see here, I get big number, 56,250. Again, kilogram per meter per second, or not per, sorry, kilogram meter per second. And again, because momentum is a vector, it's going to be east, just like our velocity is. So, and there we go. So that's just finding momentum. Now you can see our title here is momentum and impulse. And what an impulse is all about is that when an object encounters a change in momentum, and again, that's a vector symbol there, but that delta, again, delta anytime in math and science refers to change. Then you have a change in momentum, then the object undergoes what we call an impulse. And so an impulse is a force which is applied over a specific amount of time. And so therefore, mathematically, how we're going to write that is that an impulse is equal to a change in momentum. So delta for change, we have our rho symbol for momentum. It's a vector, and it's determined by a force that is also a vector times time, or delta t. Now, another way of looking at the change in momentum, the change in anything, is that we can take the final momentum, so rho f, minus the initial momentum, rho I. And again, that would be equal to our F times delta T. Now I can even further break this formula down because, again, with momentum, when you have the final momentum minus the initial momentum, momentum is, again, mass times velocity. And so the final momentum would be the mass times the final velocity. And same thing with our initial momentum. It would be the mass times the initial velocity. So that is another way to figure out an impulse, a change in momentum. And again, it is equal to our force times delta t. And there we go. So basically we got 1, 2, 3 formulas that are all the same but can be expressed differently. All right, now let's try a couple questions. For example, we have example 2 here, a 1,400 kilogram car moving west with a velocity of 15 meters per second, collides with a snowbank, that's not good, and is brought to rest in 0.4 seconds. Find the force exerted on the car during the collision. All right, so here we go. Again, I'm going to write down the information that I have, and so I always like to read my examples once and then read them again to get the information. And so right out of the bat, it says a 1,400 kilogram car. So again, that is our mass, is 1,400 kilograms, again in our standard units. Is moving west, okay, with a velocity of 15 meters per second. So that would be our VI. And again, we have it at 15 meters per second. Again, velocity is a vector, and so I've got to put the symbol in there, west. It is brought to rest, in 0.4 seconds. Well, first of all, when you're brought to rest, that's telling me that the final velocity is in fact 0. And the time that that's happening in is very quickly 0.4 seconds, which is again in our standard units. And what we want here is our force. All right, so and again, our velocity is a vector, so let's put a vector symbol in there. All right, so if I go back and look at one of my formulas that involves these variables, where we have VI, VF, the mass, and T, the time that's gone by, we could also call it delta T, same thing, how much time has gone by, or the change in time. And so I look, and it looks like I'm going to use my last formula here, all right, because I have the time. I have the VI, the mass, the VF, and the mass. So there we go. We'll use that formula right there. Let's see if I can even capture it here. Give it a chance. And we go back. Hey, there we go. And so there's the formula we're going to use. All right, but now I have direction when it turns into velocity here. So again, I'm going to designate one direction positive, one direction negative. Now, I always generally make east positive, so I'm going to keep doing that. And I'm also going to designate west as a negative direction. All right, so now to substitute into my formula. First off, our mass here is 1,400 kilograms. Our final velocity is 0. All right, then we have a minus sign. Again, the mass there is 1,400 kilograms. Whoops, just 1,400. And our VI there is 15 meters per second west. So because it's west, I'm going to put in a minus 15. All right, and then on the other side here, we're trying to find the force. And I know the time is 0.4 seconds. All right, so, well, just simplifying things. 1,400 times 0, that's nothing. That's gone. That's 0. Okay, and then I have a minus sign. And then I have 1,400 times minus 15, which is a minus 2,000. Oh, actually, no, 21,000. And there we go. Equals, and whoops, equals. And I got F times 0.4. Well, I always put the number in front. So 0.4 times F. No big deal there. All right, and continuing on. All right, let's get down to the next level. There we go. All right, 2 minus signs there. Well, then it just looks like I'm going to have a 21,000. Equals my 0.4 times F. All right, now again, we're trying to find the force exerted. And so I'm going to get F by itself by dividing both sides by 0.4. And what I do to one side, I can do the other here. And if I take 21,000 and divide it by 0.4, I end up getting, let's see here, just got my calculator out. Okay, I'm getting a big number here. So our force is equal to 52,500 newtons. Now it is positive, and so That means, again, I've said east is positive, west is negative. It looks like the force is applied in the east direction. And again, a force here is a vector. So let's put a little vector symbol on that. Now that makes sense. If the car was moving west, to stop it, we would need a force in the opposite direction, which would be east. So it all makes sense. Again, watching our signs. All right, let's see here. Try another one. My favorite player, example 3, Connor McDavid applies a force of 30 newtons east, so this time we have a force, on a hockey puck that's 168 grams, that's true, in 0.2 seconds. If the initial velocity of the puck is 5 meters per second west, okay, find the change in momentum on the puck, or impulse. Again, change in momentum is an impulse. It should say on the puck there, but it's in the puck or on the puck. All right, so again, I'm going to write down some things that we have here that will help us out. So again, the applies a force, so we know the force is 30 newtons east. Let's get that down, all right. The hockey puck has a mass of 168 grams. Now that is not in our standard units. And again, to get grams into kilograms, you have to divide by 1,000. And so it would be, let's see here, take 1.168 divided by 1,000, I get 0.168 kilograms. So again, got to be in our standard units there. All right, time that went by, okay, we got a 0.2 seconds. And we have initial velocity, actually, VI, which is our 5 meters per second to the west. Okay, there we go. And now it says here in A, find the change in momentum or the impulse on the puck. Now again, the impulse formula is delta rho, change in momentum, is equal to force, which is a vector, so is VI here, okay, times delta T or T. Okay, well, we have both of those, so I'm going to, well, plug in my information here. Don't have to do anything special here because I already found everything. All right, so my force, we're going to have our 30 newtons east. So let's put that in there, 30 newtons. Get our direction, east. All right, and I'm going to multiply that by our time, which is 0.2 seconds. Whoops, there we go. I don't need the seconds in there. All right, now if I multiply those two numbers, we end up with a change in momentum, the impulse, if you will. 30 times 0.2 is 6. And it should be 6 kilograms. Again, the units don't really make sense, but they are there. Kilogram meter per second. What we do really need, though, is our direction, which is east. And there we go. There's our change in momentum, our impulse. We're not done yet because we want to find out a little bit more about what happens here with Connor. Is that we get to B. We want the puck's final velocity. Now I believe we're going to use the same formula that we just used prior to in our last question. So I'm going to go back again and scoop that up, that question. So there we go. Let's get that. Control C. We'll use that. All right, and here we go. So there we go. Because again, let me check to make sure I have everything. We have the initial velocity. That's true. We've got the mass of the puck. We know the force, and we know the change in time. All right, so we got everything but what we're looking for, and that is our final velocity. All right, so now I'm going to substitute in my values. All right, so let's see here again. Our mass is, let's see here, we got 0.168. All right, times our final velocity, which we don't know, so I'll put a VF there, minus the initial, or the mass again, which is 0.168, times our initial velocity. Let's go out. What was that again? Oh, I got a direction here, 15 or 5 meters per second west. So as I mentioned before, again, I'm going to go with east is positive. All right, and that means the direction I'm dealing with here, west, is negative. Okay, so let's get back in here. So that means Our initial velocity was 5 meters per second west, so I'm going to plug in a -5 here. And again, our force, let's go back up. Our force was 30 newtons east. So I'm going to put in a positive 30, right? Because I said east was positive. And our time, I believe, oh, better look up again. I'm going to mess up. 0.2 seconds. All right, so let's put that in there. 0.2 seconds. All right, now to do a little bit of math. All right, so we got the 0.168 times VF. And then I have a minus 1.68 times a -5. So I'm going to get a positive here. And if I take those two numbers and I multiply them, what do I end up with here? It's going to be small. Yeah, I get to two decimal places, 0.84. And that's going to be equal to 30 times 0.2, which case I get a 6. There we go. All right, so now, again, I'm trying to solve for VF, find the final velocity of this puck. So I'm going to move that 0.84 over to the other side. Okay, so that means I got a 0.168 VF is equal to, I got the 6 over there. This 0.84 is coming over to the other side, so it changes sides. It's going to change sign here. Okay, so then still on my left side, I got 0.168 times VF. And if I take 6 minus 0.84, it's like having $6 minus 84 cents. I get 5.16. All right, so now keep going here. Getting VF by itself, I'm going to have to divide this 0.168 off. And what I do to one side, I got to do to the other. All right, so those divide each other out, and guess what we're left over with? Our final velocity of this puck. All right, and if I take 5.16 and I divide it by 0.168, I end up with a 30.71 meters per second. It's positive, so now the puck is going in the east direction. And again, our velocity is a vector, and that's why we have direction. And there is the velocity of McDavid's the shot after it comes back. So if I look at this question, what's happening is the puck initially is moving west, so it's coming back to McDavid, and then he hits it with an impulse of 6 kilogram-meter per second east, and then afterwards that puck is moving at 30.71 meters per second the other way. And that is, again, momentum and impulse. Where, again, impulse is a change in momentum, but yet momentum itself is mass in motion.